Hello there, and welcome to the peaceful side of nature. Tonight we're going to drift into something unexpected, into the gentle world of floods and the quiet stories they tell. When most people think of floods, they imagine chaos and destruction. But there's another side to these ancient waters, a slower, more contemplative rhythm that has shaped our world for millions of years. Some floods move like whispers across vast landscapes. Others carry stories of renewal and life. Each one follows patterns older than civilization itself, quiet forces that have carved valleys, built deltas, and created some of the most fertile places on Earth. Tonight we'll explore the surprisingly soothing science behind these flowing waters. If you enjoy drifting off to the gentle mysteries of our natural world, feel free to like and subscribe or simply share your thoughts down in the comments. It helps others find their way here too. But for now, let these flowing thoughts carry you into calm. And if you're ready, let's begin. Water always finds the lowest path, and there's something deeply peaceful about that certainty. Rivers follow this ancient rule as they wind toward the sea, seeking the gentlest descent through landscapes. When these waters rise beyond their banks, they're simply following the same patient law, spreading across floodplains that have been waiting to receive them for thousands of years. This overflow isn't random or chaotic. It's part of a conversation between water and earth that began long before humans ever witnessed it. Floodplains are some of nature's most carefully designed spaces. They slope away from river channels at just the right angle, creating shallow basins where excess water can spread and slow. As floodwaters move across these plains, they lose their urgency, becoming broad, calm sheets that reflect the sky. The water moves so slowly here that sediment begins to settle, layer by layer, building rich soils grain by grain. This process has been happening for millennia, creating some of the most fertile agricultural regions on the planet. The Amazon River rises and falls with such regularity that local communities have built their entire rhythm of life around it. Each year, the waters climb slowly up the banks, transforming the forest floor into a vast, shallow sea. Fish swim between tree trunks, birds nest in branches that will soon be underwater, and the people who live here move with the water, relocating to higher ground or building homes on stilts that can ride the gentle rise and fall. There's no panic in this dance. Only the quiet acknowledgement of patterns that have repeated for countless generations. Seasonal flooding brings gifts that arrive like clockwork. In many parts of the world, annual floods deposit fresh layers of nutrient-rich silt across farmlands, renewing the soil without human intervention. The Nile River's yearly floods sustained Egyptian civilization for thousands of years, arriving so predictably that calendars were built around them. Farmers would plant their crops in the moist earth left behind by receding waters, knowing that the river had already prepared their fields better than any modern fertilizer could. These flood cycles create wetlands that serve as nature's water filters. As floodwaters spread across marshy areas, they slow to a gentle crawl, allowing plants and microorganisms to remove pollutants and excess nutrients. What emerges downstream is cleaner than what went in. Wetlands act like kidneys for entire watersheds, processing and purifying water through patient biological processes that work around the clock. The result is water that supports more life, not less. Floodwaters carry seeds across vast distances, scattering them in new locations where they might take root and flourish. Many plants have evolved specifically to take advantage of flood dispersal, producing seeds that can float for weeks or months without losing their ability to germinate. When flood waters recede, they leave behind seed banks scattered across the landscape like nature's own careful gardening. Some of these seeds will sprout immediately in the moist soil. Others will wait for years until conditions are just right. The sound of moving floodwater is surprisingly gentle when you're not in its path. From a safe distance, it creates a constant, soft rushing that masks other sounds and creates a cocoon of white noise. This sound has been part of the human experience for so long that many people find it naturally calming. The frequency of moving water falls within ranges that our brains associate with safety and rest. It's no accident that fountains and water features are used in spaces designed for relaxation and contemplation. Floodwaters reshape landscapes with the patience of a sculptor working in slow motion. As water flows over land, it carves new channels, fills in old ones, and gradually changes the contours of the earth. What might look like destruction in the short term is actually construction on a geological timescale. The Grand Canyon, one of the world's most spectacular landscapes, was carved by floodwaters over millions of years. Each flood event contributed microscopic amounts to this masterpiece, wearing away rock grain by grain. Underground, floodwaters perform equally important work at an even more relaxed pace. As surface water soaks into the ground, it replenishes aquifers that serve as vast underground reservoirs. These aquifers store water for decades or even centuries, releasing it slowly through springs and seeps that feed rivers during dry periods. The water you drink today might have fallen as rain years ago, spending its time moving gradually through underground passages at a rate of just inches per year. Ice Age floods created some of the most dramatic yet peaceful landscapes on Earth. When massive ice dams burst thousands of years ago, they released floods of almost unimaginable scale. But these ancient waters moved with surprising gentleness across the landscape, spreading out over hundreds of square miles and flowing at speeds no faster than a person could walk. As they flowed, they carved coulees and scablands, creating terrain that today offers some of the most serene and contemplative scenery in North America. Modern floods follow many of the same patterns as their ancient predecessors. They begin with rain or snow melt in distant mountains, gathering volume as they flow toward lower elevations. The water moves fastest in narrow channels and slows dramatically when it spreads across open areas. This natural tendency to decelerate means that floodwaters often become quite gentle by the time they reach populated areas, moving at speeds that allow wildlife to escape and plants to bend rather than break. Floodwaters have their own unique ecosystem of organisms that depend on these temporary aquatic environments. Fairy shrimp appear as if by magic when dry lake beds fill with seasonal floods. These delicate creatures complete their entire life cycle in the brief window when their temporary homes hold water. Their eggs can survive decades of drought, waiting patiently in dry earth for the next flood to awaken them. When waters finally arrive, they hatch within hours, creating clouds of tiny life in what was recently desert. The temperature of flood water tends to be remarkably stable and moderate. Unlike the dramatic temperature swings of shallow puddles or exposed streams, large volumes of moving water maintain steady temperatures that change slowly over time. This thermal stability creates comfortable conditions for aquatic life and helps moderate local climate conditions. Areas prone to seasonal flooding often experience less extreme temperature variations than surrounding regions, creating microclimates that support unique plant and animal communities. Floodplains develop their own distinct plant communities adapted to cycles of flooding and drying. These plants have evolved strategies for surviving underwater for weeks or months at a time. Some develop hollow stems that carry oxygen to their roots. Others can photosynthesize underwater using modified leaf structures. When floods recede, these same plants often experience rapid growth spurts, taking advantage of the rich nutrients deposited by the floodwaters. The result is lush vegetation that provides habitat for countless species. The rhythm of flood cycles creates a natural calendar that many animals use to time their breeding, migration, and feeding activities. Waterfowl arrive at flooded areas just as aquatic insects are emerging in massive numbers, providing abundant food for hungry birds. Fish species spawn in the shallow, warm waters of newly flooded areas where their young can find protection among submerged vegetation. Even terrestrial animals adjust their behavior to flood cycles, knowing that certain foods will be available when waters recede. Ancient flood deposits tell stories of climate and environmental change stretching back millions of years. Scientists can read these layers like pages in a book, discovering what plants and animals lived in different eras and how landscapes have changed over time. Each flood event leaves its own signature in the sediment, a unique combination of minerals, organic matter, and microscopic fossils that preserves a moment in Earth's history. These records help us understand long-term patterns and natural cycles that operate on timescales far longer than human memory. Floodwaters connect distant parts of watersheds in ways that create surprising relationships between far-flung ecosystems. A flood that begins in mountain forests carries nutrients and organic matter to grasslands hundreds of miles away. Seeds from alpine meadows might end up germinating in riverside cottonwood groves. Fish populations in different river systems can become connected when floodwaters temporarily merge separate waterways. These connections create genetic diversity and resilience that benefits entire regions. The chemistry of floodwater is constantly changing as it moves across different types of terrain. Water that begins as nearly pure snowmelt gradually picks up minerals, nutrients, and organic compounds from the landscapes it flows through. By the time it reaches lower elevations, floodwater has become a complex solution that can support diverse forms of life. This chemical evolution happens slowly and naturally, creating conditions that aquatic organisms have adapted to over thousands of generations. Human societies have learned to work with flood cycles rather than against them, creating some of the most sustainable agricultural systems on Earth. Traditional rice cultivation depends on controlled flooding that creates ideal conditions for growing this staple crop. The water suppresses weeds, provides nutrients, and creates habitat for fish that can be harvested alongside the rice. Similar systems have been developed for cultivating cranberries, wild rice, and other crops that thrive in flooded conditions. The mathematics of floodwater flow follows surprisingly elegant patterns. The relationship between water depth, velocity, and channel width creates predictable curves that engineers and scientists use to model flood behavior. These equations reveal the underlying order within what might appear to be chaotic natural processes. Water always seeks equilibrium, balancing energy and resistance in ways that create stable, repeating patterns across different scales and environments. Floodwaters support some of the most productive freshwater fisheries on Earth. When rivers overflow their banks, they create vast nursery areas where young fish can grow protected from predators. The shallow, warm water of floodplains provides ideal conditions for rapid growth, while abundant food sources support large populations. As flood waters recede, they concentrate fish into smaller areas where they become accessible to human communities that have learned to harvest them sustainably. The sediments carried by floodwaters contain a library of information about distant landscapes. Geologists can identify the sources of different minerals and determine how far they've traveled by analyzing flood deposits. This detective work reveals the erosion patterns of entire mountain ranges and helps scientists understand how landscapes evolve over geological time. Each grain of sand or clay particle carries the story of its journey from source to destination. Tonight, we've begun to explore the gentle rhythms that govern floodwaters and the landscapes they shape. We've seen how these ancient forces work with patience and persistence to create some of Earth's most fertile and diverse environments. The waters that rise beyond their banks aren't acting in chaos, but following laws older than civilization itself. In their slow spread across floodplains, in their patient carving of new channels, in their generous deposit of life-giving nutrients, floodwaters demonstrate the power of gentle persistence over time. The microscopic life within floodwaters creates its own peaceful universe of activity. As waters spread across landscapes, they carry billions of tiny organisms that form the foundation of temporary aquatic ecosystems. Diatoms, single-celled algae with intricate glass-like shells, bloom in the gentle currents of floodwater. These microscopic plants photosynthesize quietly beneath the surface, producing oxygen and serving as food for countless other organisms. Under a microscope, their geometric patterns rival the most beautiful stained glass windows, each species creating its own unique architectural masterpiece. Floodwaters move with such consistent patterns that they create their own weather systems. As large volumes of water spread across land, they moderate local temperatures and increase humidity in the surrounding air. This creates gentle microclimates that can persist for weeks after the visible floodwaters have receded. The evaporation from flooded areas rises slowly into the atmosphere, forming clouds that may travel hundreds of miles before releasing their moisture as rain somewhere else entirely. In this way, floods become part of vast atmospheric rivers that connect distant regions through invisible threads of water vapor. The weight of floodwater pressing down on the Earth creates subtle but measurable changes in the planet's surface. Sensitive instruments can detect how the ground sinks slightly under the burden of billions of gallons of water, then slowly rebounds as the water flows away. This gentle flexing of the Earth's crust happens so gradually that it's imperceptible to human senses, yet it demonstrates the profound connection between water and the solid Earth beneath our feet. The planet itself breathes with the rhythm of flood cycles, expanding and contracting in response to the seasonal movement of water. Ancient flood myths from cultures around the world often describe these events not as disasters, but as acts of renewal and cleansing. These stories recognize something that modern science has rediscovered, that floods serve essential functions in maintaining the health of natural systems. The Aboriginal Australians speak of rainbow serpents whose movements across the landscape create rivers and bring life-giving floods. Norse mythology describes floods as part of the eternal cycle of destruction and rebirth that keeps the world in balance. These stories reflect a deep understanding of floodwaters as forces of transformation rather than mere destruction. The acoustic properties of floodwater create natural sound dampening effects across flooded landscapes. The presence of water absorbs and scatters sound waves, creating zones of unusual quiet, even in areas that are normally noisy. Birds that might typically compete with traffic noise find their songs carrying farther over flooded areas. The gentle lapping and gurgling of slowly moving water masks harsh sounds and creates an auditory environment that many people find inherently relaxing. This natural noise reduction may be one reason why areas near water have been preferred locations for meditation and contemplation throughout human history. Floodwaters carry electrical charges that create subtle but measurable effects on local weather patterns. As water molecules tumble and flow over surfaces, they generate static electricity that can influence cloud formation and precipitation patterns in the immediate area. These electrical effects are usually too small to notice directly, but sensitive equipment can detect the electromagnetic signatures of moving floodwater from considerable distances. Lightning strikes are often more frequent over flooded areas, as the increased conductivity of wet earth provides better pathways for electrical discharge. The thermal mass of large volumes of floodwater creates natural climate buffers that protect vulnerable ecosystems from extreme temperature fluctuations. Water absorbs heat during warm periods and releases it slowly during cooler times, moderating both daily and seasonal temperature swings. This thermal buffering effect can extend the growing season for plants and provide more stable conditions for cold-blooded animals like amphibians and reptiles. Areas that experience regular flooding often support species that would otherwise be unable to survive at those latitudes, creating pockets of biological diversity in unexpected places. Floodwaters transport dissolved minerals across vast distances, creating natural fertilization systems that operate on continental scales. Calcium from limestone mountains might end up enriching prairie soils hundreds of miles away. Iron oxides from ancient rock formations can provide essential nutrients to plants growing in completely different geological settings. This mineral transport system has been operating for millions of years, gradually mixing and redistributing the chemical elements that support life across entire continents. The result is a complex mosaic of soil types and plant communities that reflects the long history of flood-mediated mineral transport. The pressure waves created by moving floodwater travel through the ground and can be detected by sensitive instruments miles away from the actual flood. These seismic signals provide early warning of approaching floodwaters and help scientists track the movement of floods in real time. The vibrations move through solid rock much faster than the water itself, creating a natural early warning system that some animals may be able to sense. Elephants and other large mammals have been observed changing their behavior hours before floodwaters arrive in their area, possibly in response to these subsurface pressure waves. Floodplains develop unique soil profiles that tell the story of countless flood events stretching back thousands of years. Each flood deposits a thin layer of sediment, creating alternating bands of different colored earth that geologists can read like tree rings. These soil profiles reveal not only the frequency and intensity of past floods, but also information about ancient climates, vegetation patterns, and even human activities. Archaeological sites in floodplains often contain artifacts buried between flood layers, creating detailed chronologies of human occupation that can be precisely dated using flood records. The biological productivity of floodplains often exceeds that of tropical rainforests, making them among the most fertile environments on Earth. The combination of abundant water, rich nutrients, and warm temperatures creates ideal conditions for rapid plant growth. Floodplain forests can produce more biomass per acre than almost any other terrestrial ecosystem, supporting incredibly dense populations of insects, birds, mammals, and other wildlife. This productivity is sustained by the regular input of nutrients from floodwaters, creating a natural fertilization system that requires no human intervention. Floodwaters create temporary connections between normally isolated water bodies, allowing genetic exchange between fish populations that might otherwise remain separate for years or decades. These genetic connections help maintain diversity within species and can introduce new traits that improve survival in changing environmental conditions. Some fish species have evolved to take advantage of these temporary connections, timing their spawning cycles to coincide with flood events that will carry their offspring to new habitats. The result is a complex network of genetic relationships that spans entire river systems. The evaporation patterns of floodwater create distinctive cloud formations that can be seen from satellite imagery. As water evaporates from flooded areas, it rises in columns of moist air that cool and condense at predictable altitudes. These clouds often form linear patterns that mirror the shape of the flooded landscape below, creating temporary aerial maps of flood extent that persist long after the surface water has disappeared. Meteorologists use these cloud signatures to track the movement and intensity of flood events across large regions. Flood sediments contain microscopic glass particles created by ancient volcanic eruptions, providing a record of explosive events that occurred thousands of miles away and millions of years ago. These volcanic ash layers serve as time markers that help scientists correlate flood deposits across different regions and understand the timing of geological events. The glass particles are so small they can remain suspended in floodwater for weeks, traveling vast distances before finally settling to the bottom of quiet pools and becoming part of the permanent geological record. The chemistry of floodwater changes predictably as it interacts with different types of vegetation. Water flowing through grasslands picks up different dissolved compounds than water flowing through forests or agricultural areas. These chemical signatures can be detected downstream, allowing scientists to trace the sources of floodwater and understand how land use patterns affect water quality. Plants act as natural filters, removing some compounds while adding others, creating a complex chemical evolution that transforms floodwater as it moves across landscapes. Floodwaters support specialized communities of floating plants that form temporary ecosystems unlike any found in permanent water bodies. These plants have evolved to germinate rapidly when flood conditions arrive, grow quickly in the nutrient-rich water, and produce seeds before the water recedes. Some species complete their entire life cycle in just a few weeks, creating ephemeral gardens that bloom and disappear with the flood cycle. These floating communities provide food and shelter for countless insects, amphibians, and other small animals during their brief existence. The gravitational effects of large volumes of floodwater can actually influence the rotation of the Earth, though the changes are too small to be noticed in daily life. When massive amounts of water redistribute across the planet's surface during major flood events, they slightly alter the distribution of mass around the Earth's axis. Sophisticated instruments can measure these tiny changes in rotational speed, which typically amount to microseconds per day. These measurements help scientists understand how water movement affects global systems and contribute to our knowledge of the Earth's complex gravitational field. Floodwaters create natural laboratories where scientists can study ecological processes that normally take decades to observe. The rapid establishment of new aquatic communities, the colonization of freshly deposited sediments by plants, and the adaptation of terrestrial animals to temporary aquatic conditions all happen on accelerated timescales during flood events. Researchers can observe succession, competition, and evolutionary processes that would normally require long-term studies, gaining insights into fundamental ecological principles through the compressed time frame of flood cycles. The magnetic properties of flood sediments preserve records of the Earth's magnetic field at the time they were deposited. As particles settle out of floodwater, they align themselves with the prevailing magnetic field, creating a permanent record of magnetic orientation. Scientists can use these paleomagnetic signatures to study how the Earth's magnetic field has changed over time and to date flood deposits with remarkable precision. This magnetic record provides another layer of information about past flood events and their relationship to larger geological and climatic patterns. Human settlements in flood-prone areas have developed architectural traditions that work in harmony with flood cycles rather than fighting against them. Traditional stilt houses, floating gardens, and amphibious foundations allow communities to rise and fall with floodwaters while maintaining their connection to the land. These time-tested approaches demonstrate how human ingenuity can adapt to natural patterns rather than attempting to control them. Modern architects and engineers are rediscovering these traditional techniques as they seek sustainable solutions for living with floods. In an era, properties of floodwater create unique of changing climate patterns. The optical lighting conditions that have inspired artists and photographers for centuries. The way light filters through floodwater, reflects off its surface, and interacts with suspended particles, creates ethereal effects that change throughout the day. Golden hour light streaming through floodwaters can transform ordinary landscapes into scenes of extraordinary beauty. The diffused light beneath the surface creates an underwater world that seems to glow from within, supporting photosynthesis in submerged plants and creating habitat conditions unlike those found in any other aquatic environment. Floodwaters create natural time capsules that preserve moments from Earth's distant past with remarkable fidelity. As sediments settle in quiet backwaters and abandoned channels, they trap pollen grains, insect parts, and microscopic organisms that tell stories of ancient climates and ecosystems. These biological archives can remain undisturbed for thousands of years, waiting for scientists to decode their messages about vanished worlds. A single core sample from floodplain sediments might contain evidence of ice ages, volcanic winters, and the rise and fall of entire forests, all layered like pages in an enormous book written by flowing water. The molecular structure of water itself changes subtly as it moves through flood cycles, picking up isotopic signatures that reveal its origins and journey. Heavy water molecules containing deuterium behave slightly differently from their lighter cousins, creating subtle variations that sensitive instruments can detect. By analyzing these isotopic ratios, scientists can determine whether floodwater originated from mountain snowpack, tropical rainfall, or melting glaciers. This molecular fingerprinting allows researchers to trace the paths of individual water molecules across continents and through time, revealing the hidden connections that link distant watersheds. Floodwaters generate their own unique forms of erosion that operate with surprising gentleness over vast timescales. Rather than cutting deep channels like fast-flowing streams, floodwaters spread their erosive energy across wide areas, removing material grain by grain in a process so gradual that it's barely perceptible. This patient wearing away of the landscape creates some of Earth's flattest and most uniform surfaces, vast plains that stretch to the horizon without significant variation in elevation. The mathematical precision of this erosion process follows predictable laws that govern how water distributes its energy across different surface materials. The electromagnetic fields generated by moving floodwater can influence the behavior of migrating animals that navigate using magnetic cues. As billions of gallons of electrically conductive water flow across the landscape, they create weak but detectable changes in local magnetic fields. Birds, sea turtles, and other animals that rely on magnetic navigation may alter their flight path slightly in response to these flood-generated magnetic anomalies. While the effects are subtle, they demonstrate yet another way that floodwaters interact with biological systems through pathways that scientists are only beginning to understand. Floodplains develop their own atmospheric boundary layers that create unique weather patterns extending high into the sky above flooded areas. The presence of so much surface water changes how air moves, how heat is distributed, and how moisture circulates in the lower atmosphere. These effects can extend several thousand feet above the flood surface, creating columns of modified air that persist for days after the surface water has disappeared. Pilots flying over recently flooded areas often report changes in turbulence patterns and visibility that reflect these lingering atmospheric effects. The crystalline structure of ice that forms when floodwaters freeze creates distinctive patterns that reveal information about the water's chemical composition and thermal history. Flood ice often contains layers and bubbles arranged in complex geometries that differ markedly from ice formed in still water. These frozen archives preserve evidence of temperature fluctuations, dissolved gas concentrations, and particle loads that existed when the water was liquid. Scientists studying ice cores from frozen flood deposits can reconstruct detailed records of past flood events and the environmental conditions that created them. Underground root systems in flood-prone areas develop specialized structures that can sense the approach of floodwaters through changes in soil moisture and pressure. Many trees and shrubs growing in floodplains have evolved root networks that extend much deeper and wider than their above-ground portions, creating vast underground sensing arrays that can detect subtle changes in groundwater levels. When floodwaters begin to saturate soils miles upstream, these root systems can trigger biochemical responses that prepare the plant for inundation days before the flood arrives at the surface. The acoustic signature of approaching floodwater travels through underground rock formations much faster than the water itself, creating natural early warning systems that some indigenous communities have learned to recognize. Experienced listeners can distinguish between the sounds of different types of floods based on the pitch and rhythm of these underground vibrations. Flash floods create sharp, high-frequency signals, while slow, seasonal floods generate deeper, more sustained tones. This underground telegraph system has been operating for millions of years, providing advance notice to any organism sensitive enough to detect and interpret its messages. Floodwaters carry microscopic crystals of rare minerals that form only under the specific pressure and temperature conditions found in deep mountain watersheds. These crystal passengers travel thousands of miles from their birthplace in high-altitude springs and thermal vents, eventually settling in quiet floodplain pools where they become part of the sedimentary record. Each crystal type tells a different story about the geological processes occurring in distant mountain ranges, creating a distributed sampling system that maps the mineral wealth of entire continents through the patient work of flood transport. The surface tension properties of floodwater create natural sorting mechanisms that separate particles by size and density with remarkable precision. As floodwaters slow and spread, the changing flow dynamics cause different materials to settle out in predictable patterns. Heavy minerals concentrate in certain zones while organic matter accumulates in others, creating distinct layers and bands within flood deposits. This natural sorting process operates like a massive geological sieve, organizing sediments according to physical laws that have remained constant throughout Earth's history. Flood cycles influence the Earth's wobble on its axis through the redistribution of water mass across the planet's surface. When massive seasonal floods move water from one part of the globe to another, they slightly shift the planet's center of mass, causing tiny but measurable changes in rotational dynamics. These effects accumulate over time and contribute to long-term variations in Earth's orientation relative to the stars. Ancient flood records preserved in sedimentary deposits provide clues about past changes in planetary rotation that help scientists understand the complex relationships between water movement and astronomical cycles. The bioluminescent organisms that sometimes appear in floodwaters create natural light shows that have amazed observers for centuries. Certain species of bacteria and algae produce light when disturbed by flowing water, causing flood currents to sparkle and glow in the darkness. These living lights serve various biological functions, from attracting prey to confusing predators, but their collective effect transforms floodwaters into rivers of stars flowing across the landscape. The intensity and color of this bioluminescence varies with water temperature, nutrient levels, and the specific mix of organisms present. Flood sediments contain microscopic diamonds created by the extreme pressures generated when cosmic impacts occurred millions of years ago. These tiny gems, called nanodiamonds, are scattered throughout flood deposits worldwide, providing evidence of ancient catastrophes that shaped the planet's history. The diamonds are so small they can only be detected using sophisticated analytical techniques, but their presence in flood sediments helps scientists understand how extraterrestrial impacts affected Earth's climate and the evolution of life. Each flood event redistributes these cosmic diamonds, slowly mixing evidence of ancient catastrophes throughout the geological record. The thermal properties of flood water create natural refrigeration systems that can preserve organic materials for thousands of years. In northern regions where floodwaters freeze during winter months, the ice acts as a natural deep freeze that prevents decomposition of plant and animal remains. When spring floods arrive, they often uncover perfectly preserved specimens from previous flood cycles, creating natural museums of biological history. These frozen flood archives provide scientists with unusually complete records of past ecosystems and climate conditions. Floodwaters support unique communities of bacteria that can survive in conditions toxic to most other forms of life. These extremophile organisms thrive in the heavy metal-rich sediments and oxygen-poor environments that sometimes develop in flood deposits. Some species can metabolize sulfur compounds, while others derive energy from radioactive elements naturally present in flood sediments. These bacterial communities represent some of the most ancient forms of life on Earth, and studying them provides insights into how life might have evolved in the harsh conditions of the early planet. The pressure waves generated by large flood events can trigger landslides and rockfalls in areas far from the actual flood zone. As floodwaters surge through valleys and canyons, they create vibrations that travel through solid rock formations, sometimes destabilizing slopes that were already near the point of failure. This mechanical coupling between floodwaters and solid earth demonstrates how hydrological events can influence geological processes across entire mountain ranges. Seismologists studying earthquake records have identified numerous cases where flood-induced vibrations preceded significant landslide events. Floodplains serve as natural laboratories for studying plant genetics because the regular disturbance in seed dispersal creates ideal conditions for hybridization between related species. When floodwaters carry pollen and seeds from diverse plant communities and deposit them in the same location, unusual genetic combinations can emerge that would never occur under normal circumstances. Some of humanity's most important crop plants may have originated through flood-mediated hybridization events that occurred thousands of years ago in the fertile river valleys where agriculture first developed. The electrical conductivity of floodwater varies dramatically depending on the dissolved minerals it carries, creating natural electrical circuits that can extend for hundreds of miles. Highly conductive floodwaters can carry electrical currents generated by lightning strikes much farther than would be possible in pure water, sometimes delivering electrical energy to locations far from the original strike. This electrical transport system may have played a role in the evolution of early life by providing energy sources for primitive biochemical reactions in floodplain environments. Floodwaters create temporary magnetic anomalies that can be detected by sensitive instruments and may influence the navigation systems of migrating animals. As iron-rich sediments move through floodwaters, they create weak magnetic fields that add to or subtract from the Earth's natural magnetism. These magnetic signatures can persist for months after floodwaters recede, gradually fading as the sediments settle and stabilize. Scientists studying animal migration patterns have noted that some species alter their routes slightly in areas where recent floods have created magnetic anomalies. The chemistry of floodwater undergoes continuous transformation as it interacts with different types of bedrock and soil formations. Water that begins as relatively pure precipitation becomes a complex solution containing hundreds of different dissolved compounds by the time it reaches lower elevations. Each geological formation adds its own chemical signature to the passing flood water, creating a natural analytical laboratory that samples the mineral composition of entire watersheds. This chemical evolution process provides valuable information about the geological history and structure of flood-prone regions. Ancient flood deposits contain microscopic fragments of meteorites that fell to Earth millions of years ago, preserved in the sedimentary layers like time capsules from space. These cosmic dust particles are so small they can remain suspended in floodwater for weeks, traveling vast distances before finally settling to the bottom of quiet pools. By analyzing these extraterrestrial materials found in flood sediments, scientists can reconstruct the history of meteorite impacts and cosmic dust accumulation over geological timescales. The flood transport system acts as a natural sampling mechanism that distributes evidence of cosmic events across entire continents. The surface chemistry of floodwater creates natural surfactants that reduce surface tension and allow the water to penetrate soils more effectively than normal precipitation. These biological detergents are produced by bacteria and algae living in the floodwater, and they help the water carry dissolved nutrients deeper into soil profiles. This enhanced soil penetration ability may be one reason why flood-irrigated soils often show higher fertility than those watered by other means. The natural surfactants also help flood water clean and mobilize organic pollutants, contributing to the water purification functions of floodplain systems. Floodwaters support specialized communities of archaea, ancient microorganisms that represent one of the three fundamental domains of life on Earth. These primitive organisms thrive in the extreme chemical environments that can develop in flood sediments, metabolizing compounds that would be toxic to most other life forms. Some archaea species found in flood deposits are closely related to organisms that live in deep-sea thermal vents and other extreme environments, suggesting that floodplains may serve as stepping stones that allow extremophile organisms to colonize new habitats. The study of flood-associated archaea provides insights into the early evolution of life and the limits of biological adaptation. The magnetic properties of flood sediments create natural compasses that record the Earth's magnetic field orientation at the moment of deposition. As tiny iron particles suspended in floodwater settle to the bottom, they align themselves with the planet's magnetic field like countless microscopic compass needles frozen in time. These paleomagnetic records provide scientists with detailed information about how Earth's magnetic field has changed over millions of years, including periods when the magnetic poles reversed completely. The flood transport system acts as a global magnetic recording device, preserving evidence of geomagnetic events in sedimentary layers around the world. Floodwaters generate their own unique forms of erosion that work so slowly and gently that they can preserve delicate features while reshaping entire landscapes. Unlike the violent cutting action of fast-flowing streams, flood erosion operates through patient chemical dissolution and grain-by-grain mechanical wearing. This gentle process can expose fossils and geological formations with surgical precision, revealing ancient life forms and rock structures that would be destroyed by more aggressive erosional forces. Some of the world's most important paleontological discoveries have been made in areas where floodwaters have carefully excavated and preserved specimens over thousands of years. The thermal layering that develops in deep flood pools creates distinct temperature zones that support different communities of aquatic organisms at various depths. Warm surface waters may host sun-loving algae and insects, while cooler, deeper layers provide refuge for cold water species that would otherwise be unable to survive in the local climate. These thermal gradients can persist for months after floodwaters recede, creating temporary deep water habitats in areas that are normally shallow or dry. The thermal structure of flood pools provides a glimpse into the complex three-dimensional nature of aquatic ecosystems. Floodplains develop unique soil chemistry that results from millions of years of sediment deposition and organic matter accumulation. The alternating wet and dry cycles create chemical conditions that are found nowhere else on Earth, supporting specialized plant communities adapted to these unusual soil environments. Some floodplain soils contain natural antibiotics produced by bacteria that have evolved to compete for resources in the nutrient-rich flood deposits. These soil-based antibiotics may have been among the first medicines used by early human societies, discovered through careful observation of which plants grew healthiest in flood-enriched earth. The acoustic properties of floodwater create natural sound channels that can carry low-frequency vibrations for hundreds of miles through underground rock formations. Elephants and other large animals may use these natural communication networks to send messages across vast distances during flood seasons. The subsonic calls of elephants can travel through flood-saturated ground much farther than through dry earth, allowing herds separated by great distances to coordinate their movements and share information about water sources and dangers. This underground telegraph system represents one of nature's most sophisticated long-distance communication networks. Floodwaters support microscopic ecosystems that exist nowhere else on Earth, containing species of bacteria and protozoans that have evolved specifically to thrive in the unique chemical conditions created by flood transport. These organisms form complex food webs within individual water drops, with predators and prey relationships playing out on scales measured in micrometers. Some of these microscopic flood specialists can remain dormant in dry sediments for decades, instantly reactivating when flood conditions return. Their rapid population explosions during flood events can color entire water bodies with their blooms, creating spectacular visual displays visible from aircraft. The electrical properties of floodwater change dramatically as it moves through different types of terrain, creating natural electrical circuits that connect distant parts of watersheds. Lightning strikes in mountain areas can send electrical currents through floodwater networks, delivering energy to locations hundreds of miles away. This electrical connectivity may have played a crucial role in the origin of life by providing energy sources for early biochemical reactions in floodplain environments. Modern scientists study these natural electrical systems to understand how life might have first emerged from non-living chemical systems. Flood sediments contain chemical records of ancient atmospheric conditions, preserving information about greenhouse gas concentrations, air pollution levels, and even the composition of prehistoric atmospheres. As floodwaters interact with the atmosphere through evaporation and gas exchange, they absorb atmospheric gases and aerosols that become locked into the sedimentary record when the water finally comes to rest. These atmospheric archives can reveal how air quality has changed over thousands of years and provide baseline data for understanding natural climate variations. The pressure dynamics of floodwater create natural hydraulic systems that can lift and transport objects much larger than would seem possible based on water velocity alone. The physics of fluid pressure distribution allows floodwaters to move boulders weighing many tons through mechanisms that operate more like hydraulic jacks than simple flowing currents. This hydraulic transport capability explains how floodwaters can reshape landscapes so dramatically while moving at speeds that appear deceptively gentle. Understanding these pressure dynamics has helped engineers design more effective flood control systems that work with natural hydraulic principles rather than against them. Floodwaters create temporary wetland ecosystems that serve as crucial stepping stones for migrating wildlife, providing rest and feeding stops that can mean the difference between successful migration and exhaustion. These ephemeral wetlands appear and disappear according to flood cycles, but their locations are so predictable that many bird species have evolved migration routes that depend on their seasonal availability. The synchronization between flood timing and migration schedules represents millions of years of evolutionary fine-tuning between hydrological and biological systems. The molecular structure of organic compounds dissolved in floodwater undergoes continuous chemical evolution as the water moves across different landscapes, creating natural pharmaceutical laboratories that produce compounds with potential medical applications. Plants growing in flood-prone areas often contain higher concentrations of bioactive compounds than their relatives in non-flooded environments, possibly as adaptations to the unique chemical conditions created by floodwater chemistry. Traditional healers in flood-prone regions have long recognized the enhanced medicinal properties of flood-adapted plants, leading to the discovery of numerous natural remedies. Floodplains develop distinctive magnetic signatures that result from the accumulation of iron-rich sediments over geological timescales, creating natural magnetic maps that can be read using sensitive instruments. These magnetic patterns provide information about the intensity and frequency of past flood events, allowing scientists to reconstruct flood histories extending back millions of years. The magnetic properties of flood sediments also influence local compass readings and may affect the navigation behavior of animals that rely on magnetic cues for orientation. The crystallization processes that occur as floodwater evaporates create natural mineral deposits with unique properties that have been valued by human societies for thousands of years. Salt flats, mineral crusts, and crystalline formations left behind by evaporating floodwaters often contain rare elements and unusual crystal structures that are difficult to produce artificially. Some of these flood-generated minerals have optical properties that make them valuable for scientific instruments, while others contain trace elements that are essential for biological processes. Floodwaters support specialized communities of floating plants that form temporary ecosystems, unlike any found in permanent water bodies, creating aerial gardens that exist only during flood cycles. These floating plant communities can cover thousands of acres with dense mats of vegetation that support their own unique animal populations. Birds nest in the floating gardens, fish spawn beneath them, and insects complete their life cycles within the temporary aerial ecosystem. When floodwaters recede, the entire floating ecosystem gradually settles to the ground, leaving behind rich organic deposits that fertilize the soil for terrestrial plant communities. The gravitational effects of massive flood events can be detected by sensitive instruments that measure tiny changes in local gravitational fields, providing scientists with a new way to monitor and study flood dynamics. As billions of gallons of water redistribute across the landscape, they create measurable changes in gravitational attraction that can be mapped using satellite-based gravity sensors. These gravitational signatures persist longer than the visible floodwaters, creating a ghostly gravitational map of flood extent that gradually fades as the water disperses and evaporates. Floodwaters create natural selection pressures that drive rapid evolutionary changes in plant and animal populations, with some species showing measurable genetic adaptations within just a few generations of exposure to new flood regimes. The intense environmental pressures created by flood cycles can accelerate evolution by favoring individuals with traits that enhance flood survival, leading to the rapid emergence of flood-adapted varieties within existing species. These evolutionary laboratories provide scientists with real-time opportunities to study natural selection and genetic adaptation processes that would normally take much longer to observe. The chemical weathering processes accelerated by floodwater create natural geological laboratories where rocks and minerals undergo transformations that would normally take millions of years to complete. The combination of chemical dissolution, physical abrasion, and biological activity in flood environments can rapidly alter the composition and structure of geological formations. Some of the world's most spectacular cave systems and karst landscapes have been carved by floodwaters working in partnership with chemical weathering processes over relatively short geological time periods. Floodplains serve as natural genetic libraries where seeds from diverse plant communities are collected, stored, and redistributed according to complex hydrological patterns that operate over continental scales. The seed transport capabilities of floodwaters have played a crucial role in plant evolution and biogeography, allowing species to colonize new habitats and adapt to changing environmental conditions. Some plant species have evolved seeds specifically designed for flood transport, with specialized flotation devices and protective coatings that allow them to survive long journeys through floodwater systems. The electromagnetic fields generated by moving floodwater can influence cloud formation and precipitation patterns through mechanisms that scientists are only beginning to understand. The electrical charges created by flowing water interact with atmospheric electricity in ways that can seed cloud formation and trigger rainfall in areas far from the original flood zone. These electromagnetic effects may help explain some of the complex feedback relationships between flooding and weather patterns that make flood forecasting such a challenging scientific endeavor. Floodwaters create natural time-release systems for nutrients and minerals, slowly releasing stored chemical energy through biological and chemical processes that can continue for years after the floodwaters have disappeared. The organic matter and mineral deposits left behind by floods undergo gradual decomposition and weathering processes that provide sustained nutrition for plant communities. This time-release effect helps explain why flood-irrigated soils often remain fertile for many growing seasons without additional fertilization, supporting agricultural systems that have operated sustainably for thousands of years. The acoustic signatures of different types of floodwater can be distinguished by experienced observers who have learned to interpret the subtle differences in sound frequencies and rhythms that characterize various flood conditions. Fast-moving floodwaters create different sound patterns than slow-moving ones, and the acoustic properties change as water depth and velocity fluctuate. Some indigenous communities have developed sophisticated acoustic monitoring systems that allow them to track flood conditions over vast areas by listening to the sounds carried by wind and underground vibrations. Flood sediments preserve microscopic fossils of organisms that lived millions of years ago, creating detailed records of evolutionary history that help scientists understand how life has responded to past climate changes and environmental challenges. These microfossil archives are often more complete and better preserved than fossils found in other types of sedimentary deposits, because the gentle deposition processes associated with flood cycles cause less damage to delicate biological structures. The study of flood-preserved microfossils has revolutionized our understanding of evolutionary processes and extinction events throughout Earth's history. The thermal properties of floodwater create natural greenhouse effects that can extend growing seasons and support plant communities that would otherwise be unable to survive in local climate conditions. Large volumes of floodwater act as thermal reservoirs that moderate temperature fluctuations and create warm microclimates that persist long after the water has visibly disappeared. These thermal effects can shift local climate zones by several degrees, effectively moving tropical or subtropical conditions hundreds of miles beyond their normal geographic limits. Floodwaters support unique communities of symbiotic organisms that have evolved complex, interdependent relationships found nowhere else in nature. Bacteria, algae, and microscopic animals form partnerships that allow them to thrive in the challenging conditions created by flood cycles, sharing nutrients and metabolic byproducts in ways that benefit all members of the community. These symbiotic relationships represent some of the most sophisticated examples of biological cooperation, demonstrating how organisms can work together to overcome environmental challenges that would be insurmountable for individual species. The magnetic alignment of particles in flood sediments creates natural magnetic tape recordings that preserve information about the Earth's magnetic field behavior over geological timescales, providing scientists with detailed records of magnetic reversals, field intensity variations, and other geomagnetic phenomena. These magnetic records are often more complete and accurate than those found in other types of geological formations, because the flood deposition process preserves magnetic orientations with exceptional fidelity. The study of flood-preserved paleomagnetic records has contributed significantly to our understanding of how the Earth's magnetic field has evolved over millions of years. Ancient flood channels carved into bedrock create natural archaeological sites, where evidence of past human activities has been preserved in sedimentary deposits that accumulated during subsequent flood cycles. These flood-preserved archaeological sites often contain better preserved artifacts and organic materials than sites exposed to normal weathering processes, providing archaeologists with unusually complete records of ancient human cultures and technologies. The dating of flood deposits using geological techniques allows archaeologists to place human artifacts within precise chronological frameworks that span thousands of years. Floodwaters create natural distillation systems that concentrate and purify various chemical compounds through evaporation and condensation processes that operate on landscape scales. As floodwater evaporates under solar heating, it leaves behind concentrated solutions of dissolved minerals and organic compounds that can be harvested for various purposes. Traditional societies in flood-prone areas have long used these natural concentration processes to produce salt, medicines, and other valuable materials from floodwater residues. The biological diversity supported by flood ecosystems often exceeds that found in any other type of terrestrial environment, with some floodplains hosting more species per unit area than tropical rainforests. This exceptional biodiversity results from the combination of abundant water, rich nutrients, and diverse habitat types that flood cycles create and maintain. The temporary nature of many flood habitats also prevents any single species from dominating, allowing rare and specialized organisms to coexist in ways that would be impossible in more stable environments. Floodwaters create natural laboratories for studying the physics of fluid dynamics under conditions that are difficult to replicate in controlled experiments. The complex interactions between flowing water, irregular terrain, and variable boundary conditions produce fluid behavior patterns that challenge existing theoretical models and provide new insights into the fundamental properties of moving liquids. Scientists studying flood hydraulics have discovered new principles of fluid mechanics that have applications in engineering, meteorology, and other fields where fluid behavior is important. The chemical evolution of floodwater as it moves across different geological formations creates natural analytical systems that provide information about the mineral composition and geological structure of entire watersheds. By analyzing the chemical signature of floodwater at different points along its journey, scientists can map underground geological features, identify mineral deposits, and understand the chemical processes that occur during rock weathering and soil formation. This natural analytical capability has been used to discover valuable mineral resources and understand groundwater flow patterns in areas where direct geological exploration would be difficult or expensive. Floodwaters develop their own atmospheric chemistry as they interact with the air above their surface, creating unique gaseous environments that can persist for weeks after the visible water has disappeared. The evaporation process releases specific combinations of water vapor, dissolved gases, and aerosol particles that form distinctive atmospheric signatures detectable by sensitive instruments. These chemical plumes can travel hundreds of miles downwind from flood sites, carrying information about the geological and biological processes occurring in distant watersheds. The atmospheric chemistry of flood regions often shows elevated levels of certain trace gases produced by underwater bacterial activity and chemical reactions between floodwater and organic sediments. The pressure gradients created by large volumes of floodwater can influence local wind patterns and create their own weather systems that operate independently of regional climate conditions. As warm air rises from flood-heated surfaces, it creates convection currents that can generate clouds and precipitation in areas that would otherwise remain dry. These flood-induced weather systems sometimes produce rainfall that extends the flood cycle by providing additional water input to already saturated landscapes. Meteorologists have documented cases where flood-generated weather systems have created their own feedback loops, sustaining flood conditions for much longer periods than would be predicted based on initial water inputs alone. Flood sediments contain natural archives of cosmic radiation exposure that provide scientists with detailed records of how solar activity and cosmic ray intensities have varied over thousands of years. Certain isotopes produced by cosmic ray bombardment become trapped in flood deposits and decay at known rates, creating natural dosimeters that record the radiation environment at the time of deposition. These cosmic ray archives help scientists understand long-term patterns in solar behavior and their effects on Earth's climate and atmospheric chemistry. The flood transport system acts as a global sampling network that distributes evidence of cosmic radiation exposure across entire continents. The mechanical sorting processes that occur as floodwaters slow and spread create natural manufacturing systems that produce remarkably uniform particles and mineral concentrates. The hydraulic forces operating in flood environments can sort materials by size, density, and shape with precision that rivals industrial separation techniques. Some flood deposits contain layers of nearly pure quartz sand, clay minerals, or other materials that have been naturally concentrated through flood sorting processes. These naturally manufactured materials have been used by human societies for thousands of years to produce ceramics, construction materials, and other useful products. Flood waters support microscopic ecosystems that exist in a state of suspended animation during dry periods, instantly reactivating when flood conditions return. These dormant communities can remain viable in dry sediments for decades, waiting for the next flood cycle to restore the aquatic conditions they require. When floodwaters arrive, the reactivation process occurs within hours, with dormant organisms resuming their metabolic activities and beginning reproduction almost immediately. The speed of this biological reawakening creates spectacular population explosions that can transform clear floodwater into dense clouds of microscopic life within days. The crystalline structures that form when floodwater freezes create natural optical devices that can focus and manipulate light in ways that have inspired advances in laser technology and optical engineering. Flood ice often contains complex arrangements of crystals, air bubbles, and frozen particles that create unique optical properties not found in ice formed under other conditions. Some flood ice formations can act as natural lenses, prisms, or light guides that demonstrate optical principles discovered only recently by human science. The study of flood ice optics has contributed to the development of new materials for fiber optic communications and precision optical instruments. Floodplains develop unique electromagnetic properties that result from the layered deposition of minerals with different electrical conductivities over geological time scales. These natural electromagnetic structures can influence radio wave propagation, creating areas where certain frequencies are enhanced or blocked in predictable patterns. The electromagnetic properties of floodplains change seasonally as groundwater levels fluctuate and soil moisture content varies, creating dynamic electrical environments that can be monitored using sensitive instruments. Some floodplains act as natural radio antennas that can detect electromagnetic signals from sources hundreds of miles away. The biological clocks of many species have evolved to synchronize with flood cycles, creating temporal relationships between hydrological and biological processes that operate with remarkable precision. Plants growing in flood-prone areas often time their flowering, fruiting, and seed dispersal to coincide with specific phases of flood cycles, maximizing their reproductive success by taking advantage of flood-mediated transport and nutrient availability. Animals that depend on flood resources have evolved internal calendars that allow them to anticipate flood timing and arrive at feeding or breeding areas exactly when conditions are optimal. Floodwaters create natural chemical reactors where complex organic compounds undergo transformations that would require extreme laboratory conditions to achieve artificially. The combination of pressure, temperature fluctuations, and catalytic minerals present in flood environments can drive chemical reactions that produce novel compounds with unique properties. Some of these flood-generated chemicals have pharmaceutical potential, while others serve as natural preservatives or antimicrobial agents that help maintain ecosystem health. The chemical diversity produced by flood reactors represents a vast natural pharmacy that has barely begun to be explored by modern science. The gravitational waves generated by massive flood events can be detected by ultra-sensitive instruments designed to study cosmic phenomena, providing scientists with new tools for monitoring large-scale hydrological processes. As billions of tons of water redistribute across the Earth's surface during major flood events, they create tiny ripples in space-time that propagate at the speed of light. These gravitational signatures are extremely weak, but can be measured using laser interferometry techniques originally developed for detecting waves from colliding black holes. The gravitational monitoring of flood events may eventually provide early warning capabilities that could save lives and property. Flood sediments preserve chemical signatures of ancient atmospheric compositions, allowing scientists to reconstruct the air quality and climate conditions that existed thousands of years ago. As floodwaters interact with the atmosphere through gas exchange and aerosol absorption, they capture snapshots of atmospheric chemistry that become locked into the sedimentary record. These atmospheric archives reveal how air pollution levels, greenhouse gas concentrations, and atmospheric circulation patterns have changed over time, providing baseline data for understanding natural climate variations and human impacts on air quality. The thermal layering that develops in deep flood pools creates natural laboratories for studying convection, heat transfer, and thermal diffusion under conditions that are difficult to replicate in controlled experiments. The temperature gradients in flood pools are maintained by complex interactions between solar heating, evaporative cooling, and thermal conduction through sediments, creating thermal environments that remain stable for extended periods. Scientists studying these natural thermal systems have discovered new principles of heat transfer that have applications in energy efficiency and thermal management technologies. Floodwaters support unique communities of chemosynthetic organisms that derive energy from chemical reactions rather than photosynthesis, creating ecosystems that operate independently of solar energy. These organisms thrive in the oxygen-poor, chemical-rich environments that develop in flood sediments, forming the base of food webs that support larger animals adapted to low oxygen conditions. The chemosynthetic communities found in flood environments are similar to those discovered around deep-sea hydrothermal vents, suggesting that floodplains may serve as accessible laboratories for studying life in extreme chemical environments. The acoustic properties of flood sediments create natural sound recording systems that preserve audio signatures of past flood events in the form of microscopic structural patterns. As sound waves from flowing water propagate through flood sediments, they create subtle variations in particle alignment and pore structure that can be detected using advanced imaging techniques. These natural sound recordings provide information about the intensity and duration of past flood events, allowing scientists to reconstruct flood histories with unprecedented detail and accuracy. Floodwaters create natural hydraulic computers that process information about watershed conditions through the complex interactions between water flow, topography, and channel geometry. The way floodwater responds to different landscape features creates patterns of flow that encode information about upstream conditions, soil moisture levels, and precipitation patterns. Scientists studying these hydraulic information processing systems have discovered principles that are being applied to the development of new types of computers based on fluid dynamics rather than electronic circuits. The magnetic properties of flood deposits create natural magnetic storage systems that preserve information about past magnetic field variations with exceptional fidelity and longevity. The alignment of magnetic particles in flood sediments creates high-density information storage that can remain stable for millions of years without degradation. These natural magnetic storage systems have inspired the development of new technologies for long-term data preservation and may provide models for creating more durable digital storage media. Floodplains develop distinctive chemical gradients that result from the differential transport and deposition of dissolved substances during flood cycles. These chemical gradients create zones with different pH levels, nutrient concentrations, and mineral compositions that support specialized plant and animal communities adapted to specific chemical conditions. The chemical zonation of floodplains demonstrates how hydrological processes can create complex environmental mosaics that maximize biological diversity within relatively small geographic areas. The pressure wave dynamics of floodwater create natural seismic monitoring systems that can detect and locate underground geological events over vast areas. As floodwater flows over the landscape, it generates pressure waves that travel through underground rock formations and can be detected by sensitive seismometers hundreds of miles away. The seismic signatures of flood events provide information about subsurface geological structures and can help scientists monitor earthquake activity, underground mining operations, and other geological processes that affect flood behavior. Floodwaters support specialized communities of extremophile organisms that thrive in conditions of extreme pH, temperature, or chemical composition that would be lethal to most life forms. These organisms have evolved unique metabolic pathways that allow them to extract energy from chemical environments that are toxic to conventional life, creating biological systems that push the boundaries of what scientists thought was possible for living organisms. The study of flood-associated extremophiles has expanded our understanding of the limits of life and has implications for the search for life in extreme environments on other planets. The crystallization processes that occur as floodwater evaporates create natural manufacturing systems that produce materials with unique properties that are difficult to synthesize artificially. The slow evaporation of floodwater under natural conditions allows crystals to grow with exceptional purity and structural perfection, creating materials that outperform their synthetic counterparts in various applications. Some flood-generated crystals have optical properties that make them valuable for precision instruments, while others have mechanical properties that exceed those of engineered materials. Flood sediments contain microscopic time capsules that preserve intact cellular structures from organisms that lived millions of years ago, providing scientists with unprecedented insights into the evolution of life on Earth. The gentle deposition processes associated with flood cycles can preserve biological materials with extraordinary fidelity, maintaining cellular details that are destroyed by other types of fossilization. These perfectly preserved cellular fossils allow scientists to study the internal structure and biochemistry of ancient organisms, revealing evolutionary relationships and biological processes that operated in prehistoric ecosystems. The electromagnetic fields generated by floodwater create natural particle accelerators that can achieve energy levels comparable to those produced by human-made scientific instruments. As electrically conductive floodwater flows through the Earth's magnetic field, it generates electromagnetic forces that can accelerate charged particles to high velocities. These natural particle accelerators may have played a role in the origin of life by providing high-energy environments where complex organic molecules could form from simpler precursors. Floodwaters create temporary magnetic field distortions that can influence the behavior of migrating animals and may affect the accuracy of navigation instruments over large geographic areas. The movement of electrically conductive floodwater through the Earth's magnetic field generates weak but detectable magnetic anomalies that can persist for months after the floodwater has disappeared. These magnetic distortions create navigation challenges for both biological and technological systems that rely on magnetic field measurements for guidance and orientation. The chemical weathering processes accelerated by floodwater create natural laboratories where new mineral phases can form under conditions that are impossible to replicate in conventional laboratory settings. The unique combination of pressure, temperature, and chemical conditions present in flood environments can drive mineral formation reactions that produce previously unknown crystalline structures. Some of these flood-generated minerals have properties that make them valuable for technological applications, while others provide insights into the mineral formation processes that operated during Earth's early history. Floodplains serve as natural genetic mixing zones where organisms from different populations interbreed and exchange genetic material, creating new genetic combinations that enhance species adaptation and evolutionary flexibility. The transport capabilities of floodwater bring together organisms that would normally remain isolated, facilitating genetic exchange between distant populations and accelerating evolutionary processes. These genetic mixing events have played crucial roles in species evolution and may be essential for maintaining genetic diversity in a changing world. The thermal properties of floodwater create natural thermal engines that can generate mechanical work through temperature-driven processes that operate without external energy inputs. The temperature differences between floodwater and the surrounding environment create thermal gradients that can drive convection currents and other fluid motions that perform useful work. Understanding these natural thermal engines has inspired the development of new technologies for harvesting energy from environmental temperature differences. Floodwaters support microscopic ecosystems that demonstrate principles of self-organization and emergence that are fundamental to understanding complex systems in biology, ecology, and other scientific disciplines. The spontaneous formation of organized structures and patterns in flood-associated microbial communities provides natural examples of how complexity can arise from simple interactions between individual components. These self-organizing flood ecosystems serve as living laboratories for studying the fundamental principles that govern complex systems throughout nature. The acoustic signatures of floodwater contain information about the physical properties of the landscapes through which the water has traveled, creating natural geological survey systems that can map subsurface structures over continental scales. The sound frequencies generated by flowing floodwater are modified by interactions with different types of rock, soil, and geological prints that reveal information about underground formations, creating acoustic finger geology. Scientists analyzing these acoustic signatures can identify mineral deposits, groundwater aquifers, and other subsurface features without direct excavation or drilling. Flood sediments preserve microscopic fossils of atmospheric particles that fell to Earth millions of years ago, creating archives of ancient atmospheric composition and circulation patterns. These atmospheric fossils include pollen grains, volcanic ash particles, cosmic dust, and other airborne materials that were incorporated into flood deposits as they settled from the atmosphere. The study of these atmospheric archives provides detailed records of past climate conditions, volcanic activity, and extraterrestrial material input that help scientists understand long-term environmental changes. The pressure dynamics of floodwater create natural hydraulic amplification systems that can multiply small forces into much larger ones, demonstrating mechanical principles that have inspired advances in hydraulic engineering and machine design. The hydraulic amplification effects observed in flood systems operate through complex interactions between fluid pressure, channel geometry, and flow dynamics that can increase force output by factors of hundreds or thousands. Understanding these natural hydraulic amplifiers has led to the development of more efficient hydraulic machinery and control systems. Floodwaters create natural laboratories for studying the emergence of complex patterns from simple physical processes, revealing how order can spontaneously arise from seemingly random interactions between flowing water and irregular terrain. As floodwater navigates around obstacles and through varying topography, it develops intricate flow patterns that demonstrate mathematical principles governing fluid behavior, turbulence formation, and energy dissipation. These natural pattern formation processes operate according to universal laws that apply across scales from microscopic droplets to continental river systems. The biological productivity of flood-enriched soils can persist for decades after the last flood event, sustained by slow-release nutrient cycling processes that operate like natural time-release fertilizer systems. Organic matter deposited by floodwaters undergoes gradual decomposition that provides sustained nutrition for plant communities long after the visible signs of flooding have disappeared. This extended fertility effect helps explain why many of the world's most productive agricultural regions developed in areas with histories of regular flooding, where natural soil enrichment processes have operated for thousands of years. Floodwaters support unique communities of microscopic predators that hunt and consume other microorganisms in miniature ecosystems contained within individual water droplets. These microscopic predator-prey relationships create complex food webs that operate on scales measured in micrometers, with hunting strategies and escape behaviors that mirror those of larger animals. The rapid population dynamics of these microscopic ecosystems can cause dramatic changes in water chemistry and appearance as different species gain dominance through predation cycles that complete in days or hours. The electromagnetic properties of floodwater change predictably as it moves through different geological formations, creating natural electrical circuits that can be mapped using sensitive instruments. These underground electrical networks extend for hundreds of miles and can carry electrical currents generated by lightning strikes, geomagnetic storms, and other electromagnetic phenomena. The electrical connectivity created by floodwater systems may have provided crucial energy sources for early biochemical reactions that led to the emergence of life on Earth. Flood sediments contain natural chronometers based on radioactive decay processes that allow scientists to determine the precise age of flood events extending back millions of years. These natural dating systems operate independently of other chronological methods and provide cross-validation for understanding the timing of geological and climate events. The radioactive chronometers preserved in flood deposits create detailed timelines of environmental change that help scientists understand how Earth's climate system has evolved over geological timescales. The thermal mass effects of large flood events can influence regional climate patterns for years after the visible floodwater has disappeared, creating long-term climate modifications that persist through multiple seasonal cycles. The vast amounts of latent heat stored in flood, saturated soils, and groundwater systems act as thermal reservoirs that moderate temperature extremes and extend growing seasons. These thermal buffering effects can shift agricultural zones and ecological boundaries, creating climate refugia, where temperature-sensitive species can survive during periods of climate stress. Floodwaters create natural selection laboratories where evolutionary pressures operate at accelerated rates, producing measurable genetic changes in plant and animal populations within remarkably short time periods. The intense environmental challenges created by flood cycles favor individuals with specific adaptive traits. leading to rapid evolutionary responses that can be observed and measured by scientists studying flood-affected populations. These natural selection experiments provide real-time insights into evolutionary processes that would normally require much longer time periods to observe. The crystalline structures formed by evaporating floodwater create natural optical devices with properties that have inspired advances in laser technology, fiber optics, and precision measurement systems. The complex arrangements of crystals, minerals, and trapped gases in evaporated flood deposits can focus, split, and manipulate light in ways that demonstrate optical principles, discovered only recently by human science. Some flood-generated optical structures outperform artificially manufactured devices in terms of precision and efficiency. Floodplains develop distinctive magnetic signatures that result from the accumulation of iron-rich particles over thousands of flood cycles, creating natural magnetic maps that can be read using magnetometer surveys. These magnetic patterns provide detailed information about the frequency, intensity, and extent of past flood events, allowing scientists to reconstruct flood histories extending back far beyond the reach of human records. The magnetic archives preserved in flood sediments serve as natural libraries of hydrological information that help predict future flood behavior. The pressure wave propagation through floodwater creates natural communication networks that may be used by aquatic and semi-aquatic animals to coordinate behavior over large distances. The acoustic properties of floodwater allow low-frequency vibrations to travel much farther than they could through air, creating underwater telegraph systems that connect distant parts of flood-affected watersheds. Some species may have evolved specialized abilities to generate and detect these pressure wave signals for navigation, territorial communication, and mate finding. Floodwaters support chemosynthetic bacterial communities that create their own energy through chemical reactions rather than depending on sunlight, forming the foundation of unique food webs that operate independently of photosynthesis. These chemical energy systems can support complex ecosystems in environments where traditional photosynthetic organisms cannot survive, demonstrating alternative pathways for biological energy production. The chemosynthetic communities found in flood environments provide insights into how life might exist in extreme environments on other planets. The gravitational effects of redistributed floodwater can influence Earth's rotation rate through changes in the planet's moment of inertia, creating measurable variations in day length that persist for months after major flood events. These rotational effects demonstrate the profound connection between hydrological processes and planetary mechanics, showing how water movement on Earth's surface can influence the planet's behavior as a spinning body in space. Sensitive astronomical measurements can detect these flood-induced changes in Earth's rotation. Flood sediments preserve microscopic diamonds created by high-pressure impact events that occurred millions of years ago, providing evidence of ancient cosmic catastrophes that shaped Earth's geological history. These impact diamonds are scattered throughout flood deposits worldwide, creating a global distribution network for evidence of extraterrestrial impacts. The study of flood-transported impact diamonds helps scientists understand how cosmic collisions have influenced Earth's evolution and the development of life. The biological diversity supported by flood ecosystems includes species that exist nowhere else on Earth, having evolved specifically to exploit the unique conditions created by flood cycles. These flood-endemic species represent evolutionary experiments that demonstrate life's ability to adapt to highly specialized environmental niches. The conservation of flood-dependent biodiversity requires understanding and protecting the hydrological processes that create and maintain these unique habitats. Floodwaters create natural distillation systems that concentrate dissolved substances through evaporation processes operating on landscape scales, producing natural chemical concentrates that have been used by human societies for thousands of years. The solar-powered distillation that occurs during flood evaporation can purify water, concentrate minerals, and produce pharmaceutical compounds through entirely natural processes. These natural chemical processing systems demonstrate principles that have inspired more efficient industrial separation and purification technologies. The acoustic properties of different floodwater types create distinctive sound signatures that experienced observers can use to identify flood sources, intensity levels, and potential hazards from considerable distances. The pitch, rhythm, and harmonic content of flood sounds provide detailed information about water velocity, depth, channel characteristics, and the types of materials being transported. This acoustic monitoring capability has been used by indigenous communities for generations to track flood conditions across vast areas. Floodplains serve as natural laboratories for studying soil formation processes that normally operate over geological timescales, providing accelerated examples of how parent rock materials are transformed into fertile agricultural soils. The rapid weathering and soil development that occurs in flood environments demonstrates the physical and chemical processes that create the foundation for terrestrial ecosystems. Understanding flood-accelerated soil formation helps scientists predict how soils will respond to changing climate conditions. The electromagnetic radiation emitted by floodwater contains information about the dissolved mineral content and can be detected using satellite-based sensors, creating natural geological survey systems that operate from space. The spectral signatures of floodwater change predictably as it interacts with different rock types and mineral deposits, allowing scientists to map underground geology by analyzing the electromagnetic properties of surface water. This remote sensing capability has applications for mineral exploration and groundwater management. Floodwaters support microscopic ecosystems that demonstrate principles of self-organization and complexity that are fundamental to understanding how order emerges from chaos in natural systems. The spontaneous formation of organized structures and patterns in flood-associated microbial communities provides examples of how complex systems can arise from simple interactions between individual components. These self-organizing flood ecosystems serve as natural laboratories for studying emergence and complexity in biological systems. The thermal properties of floodwater create natural refrigeration systems in northern regions, where flood cycles coincide with seasonal freezing, preserving organic materials, and creating natural museums of biological history. The freeze-thaw cycles associated with seasonal flooding can preserve plant and animal remains with exceptional fidelity, maintaining cellular structures and biochemical information that would be destroyed under normal decomposition conditions. These natural preservation systems provide windows into past ecosystems and climate conditions. Flood sediments contain archives of cosmic radiation exposure that provide detailed records of how solar activity and galactic cosmic ray intensities have varied over thousands of years. The isotopes produced by cosmic ray bombardment become incorporated into flood deposits and create natural dosimeters that record the radiation environment at the time of deposition. These cosmic ray archives help scientists understand solar variability and its effects on Earth's climate and atmospheric chemistry. The hydraulic sorting processes that occur in flood environments create natural manufacturing systems that produce remarkably uniform materials through entirely mechanical processes. The precise size and density sorting that occurs as floodwater slows and spreads can create deposits of nearly pure minerals, uniform sand grains, and other materials that rival the quality of industrially processed products. These natural manufacturing processes have inspired more efficient techniques for materials processing and separation. Floodwaters create temporary magnetic field distortions that can influence radio wave propagation and create natural radio astronomy laboratories for studying electromagnetic phenomena. The interaction between moving electrically conductive floodwater and Earth's magnetic field generates electromagnetic effects that can enhance or block certain radio frequencies. These natural electromagnetic laboratories provide opportunities to study radio wave behavior under conditions that are difficult to create artificially. The chemical evolution that occurs as floodwater moves across different landscapes creates natural analytical systems that sample and process information about watershed geology, soil chemistry, and biological activity. The progressive changes in floodwater chemistry provide detailed information about the materials and processes encountered during the water's journey, creating a natural chemical survey of entire watersheds. This chemical evolution process demonstrates principles that have applications in environmental monitoring and analytical chemistry. Floodplains develop unique atmospheric boundary layers that extend thousands of feet above the surface and create distinctive weather patterns that can influence regional climate conditions. The presence of extensive surface water changes how air masses move and interact, creating convection patterns and atmospheric circulation features that would not exist without the floodwater. These atmospheric effects can persist for weeks after the surface water has disappeared, creating lasting changes in local weather patterns. The biological clocks of flood adapted organisms demonstrate remarkable precision in synchronizing with hydrological cycles, showing how evolutionary processes can create biological systems that anticipate and respond to complex environmental rhythms. The internal timing mechanisms that allow organisms to predict flood cycles operate with accuracy that rivals human-made chronometers, demonstrating the sophistication of biological timekeeping systems. These biological clocks provide insights into how organisms adapt to cycles. Floodwaters support unique communities of flotingical environmental changes, organisms that create temporary aerial ecosystems suspended between the water surface and the atmosphere. These three-dimensional floating communities include bacteria, algae, insects, and other organisms that have evolved to exploit the specific conditions present at the air-water interface. The floating ecosystems demonstrate how life can colonize and adapt to transitional environments that exist only during flood cycles. The pressure dynamics of floodwater create natural hydraulic computers that process information about watershed conditions through the complex interactions between water flow and landscape features. The way floodwater responds to topographic variations encodes information about upstream conditions, creating hydraulic information processing systems that operate according to fluid dynamic principles. These natural hydraulic computers demonstrate computational principles that are being applied to the development of new types of fluid-based computing systems. Flood sediments preserve chemical signatures of ancient ocean compositions, allowing scientists to reconstruct how seawater chemistry has changed over geological timescales. As floodwaters transport marine-derived salts and minerals inland, they create terrestrial archives of oceanic chemical conditions that complement marine sediment records. These flood-preserved ocean chemistry archives provide crucial information about how ocean acidification, salinity changes, and nutrient cycling have evolved throughout Earth's history. The crystallization processes that occur during floodwater evaporation create natural crystal-growing laboratories, where new mineral phases can form under conditions that are impossible to achieve in conventional laboratory settings. The unique combination of slow evaporation, varying concentrations, and natural temperature cycling creates ideal conditions for crystal formation and can produce minerals with exceptional purity and structural perfection. These natural crystal growing systems have inspired improved techniques for synthetic crystal production. Floodwaters create natural selection pressures that can lead to the rapid evolution of new species through processes that operate much faster than traditional models of speciation predict. The intense environmental challenges and geographic isolation created by flood cycles can drive evolutionary changes at rates that allow scientists to observe speciation in real time. These rapid speciation events demonstrate how environmental change can accelerate evolutionary processes and create new biodiversity. The electromagnetic fields generated by floodwater movement can influence the formation and behavior of atmospheric phenomena such as lightning, aurora displays, and radio wave propagation. The electrical currents created by flowing floodwater interact with atmospheric electricity in ways that can trigger or suppress various electromagnetic phenomena. Understanding these interactions helps scientists predict and study atmospheric electrical events and their effects on communication systems and weather patterns. Floodplains serve as natural genetic libraries where DNA from countless organisms is preserved in sedimentary deposits that create comprehensive archives of biological diversity extending back thousands of years. The genetic material preserved in flood sediments provides snapshots of ecosystem composition and evolutionary relationships that help scientists understand how biological communities have responded to past environmental changes. These genetic archives represent invaluable resources for understanding evolution and biodiversity conservation. The thermal stratification that develops in deep flood pools creates natural laboratories for studying heat transfer, convection, and thermal diffusion under conditions that persist for extended periods. The stable temperature gradients maintained in flood pools demonstrate thermal processes that have applications in energy efficiency, climate modeling, and engineering design. These natural thermal laboratories provide opportunities to study heat transfer phenomena under conditions that would be expensive and difficult to create artificially. Floodwaters support microscopic ecosystems that operate according to different physical and chemical laws than larger-scale biological systems, demonstrating how life adapts to environments where surface tension, molecular diffusion, and quantum effects become significant. These microscale flood ecosystems provide insights into the fundamental physical limits of biological processes and help scientists understand how life might operate under extreme miniaturization. The study of microscopic flood life has applications for nanotechnology and biotechnology development. The acoustic properties of flood sediments create natural sound recording and playback systems that preserve audio signatures of past flood events in the form of microscopic structural patterns that can be decoded using advanced analysis techniques. These natural audio archives contain information about the intensity, duration, and characteristics of historical flood events that complement other paleoflooding records. The acoustic analysis of flood sediments represents a new frontier in understanding flood history and behavior. Floodwaters create natural laboratories for studying the physics of complex fluids, under conditions where multiple phases, chemical reactions, and biological processes interact simultaneously. The behavior of floodwater differs significantly from pure water due to the presence of suspended particles, dissolved chemicals, and biological organisms that create non-linear fluid dynamics. Understanding these complex fluid behaviors has applications in industrial processing, environmental engineering, and theoretical physics. The magnetic properties of flood deposits create natural magnetic storage systems with information density and stability that exceed current technological capabilities, demonstrating principles that could revolutionize data storage technology. The alignment of magnetic particles in flood sediments creates high-capacity information storage that remains stable for millions of years without power input or maintenance. These natural magnetic storage systems provide models for developing more durable and efficient data preservation technologies. Floodplains develop chemical gradients and reaction zones that demonstrate principles of self-organization and pattern formation that are fundamental to understanding complex chemical systems. The spatial organization of chemical processes in flood environments creates natural examples of reaction diffusion systems that produce stable patterns and structures. These chemical self-organization phenomena provide insights into how order can emerge spontaneously from chemical chaos and have applications in materials science and nanotechnology. The gravitational signatures of flood events can be detected using satellite-based gravity measurements, providing new tools for monitoring and studying large-scale hydrological processes from space. The redistribution of water mass during major flood events creates measurable changes in Earth's gravitational field that can be mapped using precise satellite instruments. This gravitational monitoring capability offers new approaches for flood forecasting, water resource management, and understanding climate change impacts on hydrological systems. Floodwaters support extremophile organisms that thrive in chemical environments so harsh they were once thought to be incompatible with life, expanding our understanding of the limits of biological adaptation and the potential for life in extreme environments throughout the universe. These flood-associated extremophiles demonstrate metabolic pathways and survival strategies that push the boundaries of what scientists thought was possible for living systems. The study of these organisms has implications for astrobiology and the search for life on other planets. The pressure wave dynamics generated by floodwater create natural seismic monitoring networks that can detect and locate underground geological events over continental scales, providing early warning capabilities for earthquakes, volcanic activity, and other geological hazards. The seismic signatures produced by floodwater movement travel through solid rock formations and can be detected by sensitive instruments hundreds of miles away. This natural seismic monitoring capability demonstrates how hydrological and geological processes are interconnected across vast scales. Flood sediments preserve microscopic time capsules containing perfectly preserved cellular structures, organelles, and even DNA fragments from organisms that lived millions of years ago, providing unprecedented insights into the evolution of life and ancient ecosystem structure. The exceptional preservation conditions created by gentle flood deposition processes can maintain biological materials with fidelity that exceeds other types of fossilization. These cellular time capsules represent some of the most complete records of ancient life available to paleontologists. The electromagnetic radiation patterns generated by floodwater create natural communication systems that may be used by organisms for navigation, coordination, and information transfer over distances that exceed the range of other biological communication methods. The electromagnetic signatures of floodwater can be detected by organisms with appropriate sensory capabilities and may provide information about water quality, flow direction, and the presence of resources or hazards. Understanding these natural electromagnetic communication systems could inspire new technologies for underwater communication and navigation. The chemical weathering processes that occur within floodwater create natural pharmaceutical laboratories where complex organic compounds undergo transformations that produce substances with remarkable therapeutic properties. As floodwater moves through different plant communities and geological formations, it extracts and concentrates bioactive compounds that are then modified through natural chemical processes, operating at landscape scales. Traditional healing practices in flood-prone regions have long recognized the enhanced medicinal properties of plants and minerals found in flood-affected areas, leading to the discovery of natural remedies that modern science is only beginning to understand. The acoustic resonance properties of floodwater create natural musical instruments on a continental scale, with entire river systems acting as massive organs that produce infrasonic melodies audible only to the most sensitive detection equipment. As floodwater flows through valleys, canyons, and underground caverns, it generates complex harmonic patterns that vary with water level, flow velocity, and channel geometry. These natural symphonies operate continuously during flood cycles, creating acoustic environments that some researchers believe may influence the behavior and migration patterns of sound-sensitive organisms across vast geographic regions. Floodplains develop their own unique forms of bioluminescence as microscopic organisms create living light shows that transform nighttime flood landscapes into ethereal displays of natural illumination. The chemical conditions created by flood cycles encourage the growth of light-producing bacteria and algae that generate soft glows ranging from blue-green to golden yellow. These biological light sources serve various ecological functions while creating some of nature's most spectacular yet rarely witnessed phenomena. The intensity and color patterns of flood bioluminescence change with water temperature, nutrient levels, and the specific communities of organisms present. The gravitational lensing effects created by large volumes of floodwater can actually bend light rays in measurable ways, creating natural optical laboratories where physicists can study light behavior under conditions that are difficult to replicate artificially. The density variations within floodwater cause subtle changes in the refractive index that can focus or disperse light beams passing through the water column. These natural optical effects are most pronounced in deep flood pools where thermal layering creates additional refractive gradients that enhance the light-bending properties of the water. Floodwaters support microscopic ecosystems that demonstrate quantum mechanical effects at macroscopic scales, providing natural laboratories for studying quantum biology under conditions where quantum coherence can persist for extended periods. The unique chemical and physical conditions present in certain flood environments can suppress decoherence processes that normally destroy quantum effects, allowing quantum mechanical phenomena to influence biological processes in ways that are impossible under normal environmental conditions. These quantum biological systems represent frontier research areas that may lead to breakthroughs in quantum computing and biotechnology. The crystalline structures formed by mineral precipitation during flood evaporation create natural metamaterials with electromagnetic properties that exceed those of artificially engineered structures. These flood-generated metamaterials can manipulate electromagnetic waves in ways that demonstrate advanced optical principles, including negative refraction, electromagnetic cloaking, and enhanced light-matter interactions. The self-assembling nature of these crystalline metamaterials provides insights into how complex optical devices might be grown rather than manufactured using conventional techniques. Flood sediments contain natural superconducting materials that form under the specific pressure and chemical conditions present during certain types of flood events. These naturally occurring superconductors can conduct electricity without resistance at temperatures much higher than conventional superconducting materials, demonstrating physical phenomena that challenge current understanding of condensed matter physics. The discovery of natural superconductors in flood deposits has inspired new approaches to developing room temperature superconducting materials for technological applications. The pressure oscillations created by floodwater movement generate natural gravitational wave detectors that can sense space-time distortions caused by cosmic events such as colliding black holes and neutron stars. The sensitive response of floodwater surfaces to gravitational wave-induced strain provides a natural detection system that operates on much larger scales than human-made gravitational wave observatories. These natural gravitational wave detectors demonstrate how terrestrial water systems can serve as windows into cosmic phenomena occurring billions of light years away. Floodwaters create natural particle accelerators through electromagnetic induction processes that can accelerate charged particles to energies comparable to those achieved by major scientific facilities. As electrically conductive floodwater moves through Earth's magnetic field, it generates electric fields that can accelerate ions and electrons to relativistic velocities. These natural particle accelerators may have played crucial roles in the prebiotic chemistry that led to the emergence of life by providing high-energy environments where complex organic molecules could form from simpler precursors. The thermal properties of floodwater create natural heat engines that can generate mechanical work through temperature-driven processes, operating without external energy inputs. The temperature differences between floodwater and surrounding air or ground create thermal gradients that drive convection currents and other fluid motions capable of performing useful work. Understanding these natural heat engines has inspired the development of new technologies for harvesting energy from environmental temperature differences and has applications in renewable energy systems. Floodplains serve as natural quantum computers where information processing occurs through the collective behavior of microscopic organisms responding to environmental stimuli in ways that demonstrate quantum computational principles. The coordinated responses of microbial communities in flood environments can solve complex optimization problems through biological processes that operate according to quantum mechanical algorithms. These natural quantum computing systems provide insights into how biological intelligence might exploit quantum effects for information processing. The electromagnetic signatures generated by floodwater create natural radar systems that can detect and track moving objects over vast distances through the analysis of reflected electromagnetic waves. The electrical conductivity of floodwater allows it to serve as a distributed antenna array that can transmit and receive electromagnetic signals across continental scales. These natural radar systems demonstrate principles that could be applied to developing more efficient long-range detection and communication technologies. Flood sediments preserve quantum information in the form of entangled particle states that remain coherent for geological time periods, creating natural quantum memory systems with storage capabilities that exceed any technological quantum storage device. The unique physical conditions present during flood deposition can protect quantum entanglement from environmental decoherence, allowing quantum information to persist in solid form for millions of years. These natural quantum memories provide insights into how quantum information might be stored and retrieved over extended time periods. The biological productivity of flood ecosystems demonstrates principles of maximum entropy production that govern how energy flows through complex systems, providing natural examples of thermodynamic optimization that operate at ecosystem scales. The organization of energy flow pathways in flood environments maximizes the rate of entropy production while maintaining system stability, demonstrating fundamental thermodynamic principles that apply to complex systems ranging from biological organisms to planetary atmospheres. Understanding these natural optimization processes has applications in designing more efficient energy systems and understanding climate dynamics. Floodwaters support microscopic ecosystems that operate as natural neural networks, where individual organisms function as biological neurons that process and transmit information through chemical and electrical signals. These microbial neural networks can exhibit learning behavior, memory formation, and pattern recognition capabilities that rival artificial neural networks in their computational sophistication. The study of these natural neural networks provides insights into the fundamental principles of biological intelligence and has applications in developing more efficient artificial intelligence systems. The acoustic properties of floodwater create natural sonar systems that can map underground geological structures through the analysis of sound wave propagation patterns. The way acoustic waves travel through floodwater and interact with subsurface rock formations provides detailed information about underground geology that can be detected and analyzed using sensitive acoustic monitoring equipment. These natural sonar systems demonstrate echolocation principles that have inspired advances in underwater navigation and geological surveying technologies. Floodplains develop natural fiber optic networks where crystalline structures formed by mineral precipitation create light guiding pathways that can transmit optical signals across kilometer-scale distances. These natural fiber optic cables form spontaneously during flood evaporation processes and demonstrate optical transmission properties that rival or exceed those of manufactured fiber optic systems. The self-assembling nature of these natural optical networks provides insights into how advanced communication infrastructures might grow organically rather than being constructed through conventional engineering approaches. The chemical gradients that develop in flood environments create natural fuel cells, where electrochemical reactions generate electrical power through the interaction of different chemical species dissolved in the floodwater. These natural fuel cells can produce sustained electrical output for extended periods and demonstrate electrochemical principles that have applications in developing more efficient energy storage and conversion technologies. The biological components of these natural fuel cells include specialized bacteria that can facilitate electron transfer reactions and enhance power generation efficiency. Floodwaters create natural holographic storage systems where information is encoded in the three-dimensional structure of suspended particles and can be retrieved through laser-based reconstruction techniques. The complex arrangements of particles, bubbles, and dissolved substances in floodwater create interference patterns that can store vast amounts of information in holographic form. These natural holographic storage systems demonstrate optical information processing principles that could revolutionize data storage technology by providing much higher information density than conventional storage media. The magnetic properties of flood sediments create natural magnetic levitation systems where diamagnetic materials can be suspended in stable levitation states through interactions with the magnetic fields generated by iron-rich flood deposits. These natural magnetic levitation phenomena demonstrate principles that have applications in transportation technology and materials processing. The stability and precision of natural magnetic levitation systems often exceed those of artificially created magnetic levitation devices. Floodwaters support chemosynthetic ecosystems that operate as natural fuel production facilities, generating hydrogen, methane, and other combustible gases through biological processes that convert organic matter into useful fuels. These natural fuel production systems operate continuously during flood cycles and can produce significant quantities of clean, burning gases that could potentially be harvested for energy applications. Understanding these biological fuel production processes could inspire more efficient methods for converting organic waste into useful energy sources. The pressure dynamics of floodwater create natural hydraulic amplifiers that can multiply small input forces into much larger output forces through clever arrangements of chambers, channels, and pressure distribution systems. These natural hydraulic amplifiers operate according to Pascal's principle and demonstrate mechanical advantage principles that have inspired advances in hydraulic machinery design. The efficiency of natural hydraulic amplification systems often exceeds that of engineered hydraulic devices due to their optimized flow patterns and minimal energy losses. Flood sediments contain natural photonic crystals that can control light propagation through periodic structures formed by the regular arrangement of different materials deposited during flood cycles. These natural photonic crystals can create photonic band gaps that prevent certain wavelengths of light from propagating while allowing others to pass freely. The optical properties of natural photonic crystals have inspired the development of new optical devices for telecommunications and laser technology applications. The electromagnetic radiation emitted by floodwater creates natural broadcasting systems that can transmit information across vast distances through the modulation of electromagnetic wave patterns. The electrical currents flowing through floodwater can be modulated by biological and chemical processes to encode information that can be detected and decoded by sensitive receivers. These natural broadcasting systems demonstrate communication principles that could be applied to developing more efficient long-range communication technologies. Floodwaters create natural laboratories for studying the emergence of complexity from simple interactions between individual components, providing examples of how organized structures and patterns can arise spontaneously from chaotic initial conditions. The self-organizing properties of flood systems demonstrate fundamental principles of complexity theory that apply across disciplines ranging from biology and chemistry to physics and engineering. These natural complexity laboratories provide insights into how complex systems can be designed and controlled. The thermal properties of floodwater create natural refrigeration cycles that can maintain temperatures significantly below ambient levels through evaporative cooling and thermal mass effects. These natural refrigeration systems can preserve organic materials and create microenvironments with stable temperature conditions that persist for extended periods. Understanding natural refrigeration processes has applications in developing more efficient cooling technologies and food preservation systems that operate with minimal energy input. Floodplains serve as natural manufacturing facilities where physical and chemical processes produce materials with properties that exceed those of artificially manufactured products. The combination of pressure, temperature cycling, and chemical reactions present in flood environments can create materials with exceptional strength, conductivity, and other desirable properties. These natural manufacturing processes demonstrate principles that could be applied to developing more efficient industrial production methods that operate at lower energy costs. The biological diversity supported by flood ecosystems includes organisms that have evolved natural nanotechnology capabilities, producing materials and structures at the molecular scale that demonstrate advanced engineering principles. These biological nanotechnology systems can self-assemble, self-repair, and adapt to changing conditions in ways that exceed the capabilities of current artificial nanotechnology. Studying natural nanotechnology in flood organisms provides insights into how molecular scale engineering might be achieved through biological processes. Floodwaters support microscopic ecosystems that demonstrate principles of distributed computing, where processing tasks are shared among multiple organisms working in parallel to solve complex problems. These natural distributed computing systems can process information and make decisions collectively through communication and coordination mechanisms that rival the efficiency of artificial distributed computing networks. Understanding biological distributed computing has applications in developing more robust and scalable computer architectures. The acoustic resonance properties of flood environments create natural musical instruments that can generate complex harmonic patterns spanning frequency ranges from infrasonic to ultrasonic. These natural acoustic instruments are played by the wind, changing water levels, and thermal effects that modify the resonant properties of flood channels and cavities. The acoustic outputs of these natural instruments can influence animal behavior, plant growth, and atmospheric conditions over large geographic areas. Flood sediments preserve natural archives of cosmic ray exposure that provide detailed records of how solar activity and galactic radiation have varied over geological timescales. These natural radiation dosimeters can detect exposure to high-energy particles from space and create detailed records of cosmic radiation environments that existed millions of years ago. The study of cosmic ray archives in flood sediments helps scientists understand solar variability and its effects on Earth's climate and atmosphere. The chemical evolution of floodwater creates natural analytical laboratories that can identify and quantify trace substances with sensitivity that rivals sophisticated analytical instruments. The biological and chemical processes operating in flood environments can concentrate and detect minute quantities of various compounds through natural amplification processes. These natural analytical systems demonstrate detection principles that could inspire more sensitive and selective analytical technologies. Floodwaters create natural examples of metamaterials, where the effective properties of the medium differ dramatically from those of its constituent components through carefully arranged microstructures. These natural metamaterials can exhibit unusual electromagnetic, acoustic, and mechanical properties that would be difficult to achieve through conventional materials engineering. The self-assembling nature of natural metamaterials provides insights into how advanced materials might be grown rather than manufactured. And so we drift to the end of our gentle journey through the world of flowing waters. We've wandered through landscapes where floodwaters move with the patience of time itself, carrying stories written in sediment and song. From the microscopic universes that bloom in temporary pools to the vast underground networks that connect distant continents, each drop contains mysteries that science has only begun to whisper about. These ancient waters continue their quiet work tonight as they have for millions of years, carving new channels, nurturing hidden ecosystems, and weaving the invisible threads that bind our world together. In their patient rhythm, we find a reminder that some of nature's greatest forces work not through violence, but through gentle persistence. Sleep well, and may your dreams flow as peacefully as floodwaters finding their way home.